which are used. Okay, so today we are going to discuss about Moser effect. I'll share the screen. And I'll try to explain. Moser effect spectroscopy. We will study Moser spectroscopy, and in this Moser spectroscopy, we are going to discuss basic principle and what is recoil energy and what is Doppler shift, and also we see the Moser spectroscopy instrumentation. Moser spectroscopy instrumentation, in that sources and observer, and also motion devices, detections, and also reference substances and calibrations. And also in this Moser spectroscopy, we are going to discuss about the isomer shift. Isomer shift, or we will say it as chemical shift, and also quadrupole interactions and magnetic interactions, and also electronegativity and chemical shift. So let us dive into the topic, Moser spectroscopy. So, so this is uh, Moser spectroscopy was discovered by a German physicist called Rudolf Moser in 1958. Okay, this is also known as nuclear gamma resonance spectroscopy. So we can say Moser spectroscopy is also called as a nuclear gamma resonance spectroscopy. Okay, based on the resonance fluorescence of gamma radiations. So when an excited electron goes from the ground state to excited state, and it comes back to the ground state by releasing some amount of energy. That type of by releasing some amount of energy as gamma radiations, that type of effect is studied. That is called the resonance fluorescence of gamma radiations can be studied, and that is called the Moser effect actually. So when we give the energy for ground state, uh, electron, let's say, electron, what happens? It absorbs the energy and it goes to the excited state, and it won't be there for a long time, and it will come back to the ground state for the stable state, isn't it? So while coming to the stable state, it releases some amount of energy. That energy is in the form of gamma radiations. Okay, so that is studied uh, in this Moser effect. That is called actually Moser effect. Okay, so has found, so these elements used in that is uh, Fe57. This is mass number. Okay, 57 is the mass number of Fe. Isotope 57, Fe 119 tin, and antimony 121 antimony. Sorry, and 129 iodine. Okay, these are the these are some of the elements which are used for the Moser effect. Okay, has found wide applications in elucidating the nature of chemical bond in inorganic solid state chemistry and biological science. For instance, bonding in hemoglobin and oxyhemoglobin. So these elements, these type of elements are widely used in the applications of chemical bond in organic solid state chemistry and also biological science. Okay, these elements will be used in various fields of chemistry, biology, and also in the bonding of hemoglobin and oxyhemoglobin. Okay. So this is the introduction of this Moser effect. Actually, the Moser was able to achieve a recoilless emission and recoilless absorption of photons. Okay, he was able to achieve a recoilless emission. Recoilless, we will study what is recoilless. Recoilless emission and recoilless absorption of photons. Actually, that is called the Moser effect. So it provides, this uh, technique provides us the for producing and studying gamma rays. Okay, it provides us a technique for producing and studying the gamma rays whose energies are extremely well defined. Okay, this technique is used for producing and studying the gamma rays whose energy will which energies are extremely well defined. So this is the use of this Mossberg effect. So we can study the gamma rays. Okay. So for the study, we will take one of the examples of these elements and we will try to study this Mossberg effect. Let us see. So what is the basic principle? So it involves recoilless emission and absorption of gamma ray by nucleus. So it involves the basic principle of this Mossberg effect is it involves recoilless emission and absorption. Recoilless means if you if you shoot a gun, what happens? It releases the bullet and the gun comes back, isn't it? Gun comebacks, that is called recoil. Okay, we'll study that. Let us see. That is an example I have said. So involves recoilless emission and absorption of gamma ray by nucleus. Atoms in source emitting gamma rays must be same isotope as atoms in sample absorbing them. So the atoms which are in source, which are giving some energy to other element, other other atom, so that atoms must be same as that of the absorbing atom. So emitting source and absorbing source must be same. Okay, which should have same isotope. Okay, atoms in source emitting gamma rays must be same isotope as atoms in sample absorbing them. Okay, the sample and source are same here. If you consider iron, there are the bond between these irons will be same isotopes. So we'll consider that. We'll see. So what is recoil effect? Let us see. Whenever whenever a high energy particle is released from a body at rest, whenever a high energy particle is released from a body at rest, the releasing body feels a black backtick. That is, it is pushed backward just like gun. This is called the recoil effect. So whenever a high energy particle is released, so the body is at rest, which is releasing a high energy particle. So when it releases that body, it feels like back kick. Okay, it comes back and it releases like a gun. If you shot a gun, what happens? The bullet moves forward very fastly. As the bullet moves forward, it kicks back, isn't it? That's why the most of the soldiers will keep their hand stiff, isn't it? Otherwise, they'll put their gun onto the shoulder so that if it kick backs also, it doesn't hurt them. It hurts the shoulder itself. Their shoulders may be strong itself. Okay. So it is pushed backward, just like gun. This is called recoil effect. So whenever a high energy particle is released from whenever a high energy particle is released from a body at rest, the releasing body feels like a back kick that is pushed backward, like just like a gun. This is called a recoil effect, isn't it? So just now I've seen the example. Just I have said that about the gun. So in that manner, whenever an atom releases a high energy particle, it comes back, it kicks back. So that is it. That is what they are trying to say. So the energy of gamma rays is slightly less than the natural energy of transition. So the energy of gamma rays will be less than the natural energy of transition because it recoils, isn't it? So it recoils. The nucleus will recoils. That's why the gamma rays is slightly less than the natural energy of transition. Let us see. Similarly, for a nucleus at rest to absorb gamma ray. Similarly, for a nucleus, similarly for a nucleus at rest to absorb gamma ray, similarly for a nucleus at rest to absorb gamma ray, the energy of gamma ray should be slightly less than natural energy. So the the energy which is absorbing by the nucleus, the energy of that gamma ray should be slightly less than the natural energy. That energy must be less than the natural energy. Okay. So energy of recoil, ER, energy of recoil will be E gamma square by 2mc square. That is, energy of recoil is equals to E gamma square by 2mc square. That E gamma is here. E gamma is energy of gamma ray, energy between ground state and excited state. So energy of gamma ray is what? It is the energy between ground state and excited state. M is the mass of the nucleus, where small m is the mass of the nucleus. C is the velocity of the light. Okay. So recoiling effect depends upon the effective mass. So as mass increases, the recoiling effect decreases. From this formula, you can observe that energy ER, recoiling energy ER is equals to E gamma square by 2mc square. Here the recoil energy ER is indirectly proportional to m. So as the mass of the nucleus increases, what happens? Mass increases, the recoil energy decreases, isn't it? So as the recoil energy increases, the mass of the is decreased, which is low. Okay, the mass will be low when energy is high. Energy is low when mass is high. So it is indirectly proportional. So here we can say the recoiling effect depends upon the effective mass. So it depends on the effective mass. So as mass increases, the recoil effect decreases. So the recoil effect will be decreases. Okay. So for free nuclei, this resonance, that is absorption and emission of gamma rays by identical nuclei, is not observable. So for the nuclei, this nuclear resonance, that is absorption or emission of gamma rays by identical nuclei, is not observable. We cannot observe this nuclear resonance. Okay. But when nuclei is present in solid crystal, there is a little loss as recoil energy. So when nuclei will be present in a solid crystal, there will be a little loss of recoil energy. When it is in free space or not in a solid crystal, what happens? The recoil energy takes so much energy than the solid crystal type. When kept in solid, that when the nucleus is kept in solid crystal, there will be loss of recoil energy. Okay, so we try to keep the nuclei in a solid crystal so that there will be low loss of energy. Okay, so if emitting and absorbing if emitting and absorbing nuclei were in an identical chemical environment, then the transition energies would be equal and nuclear resonance. Okay. If the emitting, and absorbing, if the emitting and absorbing nuclei were identical in identical chemical environment, means the emitting nuclei and also the absorbing nuclei, which are in same identical chemical environment, the chemical environment of these two nuclei are same, then the transition energies, would be equal. The transition energy between those two will be equal and nuclear resonance. Okay. But if chemical energy environment is different, but when the chemical environment between these emitting and absorbing nuclei are different, it will cause the shift in nuclear energy loss. So there will be nuclear energy loss when the two, that is absorbing and emitting nuclei are in different chemical environment. Okay. To bring the nuclei in resonance, the energy of gamma rays is slightly changed by Doppler effect. So to bring the nuclei in resonance to the resonance, the energy of gamma rays is slightly changed. So the energy of gamma rays will be slightly changed to bring the nuclei in resonance. To bring the nuclei in resonance, the energy of gamma rays will be slightly changed by using the Doppler effect. So what Moser effect? Let's say Moser effect. Let us see. So here it involves the resonant and recoil-free emission and absorption of gamma rays by atomic nuclei bound in a solid. What is Moser effect? It involves the resonant and recoil-free emission and absorption. It involves the resonant and recoil-free emission. It is recoil-free emission. Okay, where the recoiling of emission or absorption doesn't take place. That is recoil-free emission and absorption of gamma rays, because we are keeping the nuclei in a solid, uh, uh, solid crystal. Okay, so recoil-free emission and absorption of gamma radiation by atomic nuclei bound in a solid. So we are keeping the atomic nuclei in a solid so that the recoil-free emission and absorption takes place. This is called the Moser effect. Okay. In the Moser effect, a narrow resonance for nuclear gamma radiation, gamma emission. In Moser effect, a narrow resonance for nuclear gamma emission and absorption results from the momentum of recoil being delivered to a surrounding crystal lattice rather than to the emitting or absorbing nucleus alone. So in the Moser effect, what happens? A narrow resonance for nuclear gamma emission and absorption results from the movement of recoil being delivered to a surrounding crystal rather than to emitting or absorbing nucleus alone. So there will be nuclear resonance between the emission and emission and absorption of this gamma uh, emission, radiation, the moment of recoil being delivered to a surrounding crystal lattice. So it delivers to the emission of recoil will be delivered to the crystal lattice by rather it emitting or absorbing nucleus alone. It doesn't emit or absorb, but it is delivered to the crystal lattice. Okay, in the Moser effect, as the it goes from ground state to excited state, and it excited state to ground state. When it comes back, it releases gamma energy. Then when it emits the gamma energy, it may contains a recoilness. So that is freed from the solid crystal, which is bounded in the bounded to this, when nuclei is bounded to these to the solid crystal, so it is delivered to the crystal lattice itself. Okay, by not absorbing or emitting the nucleus. When this occurs, no gamma energy is lost. So this is how the loss of gamma energy is uh, protected. Okay, when this occurs, no gamma energy is lost to the kinetic energy of recoil nuclei. So when it releases the gamma rays, it recoils. So for recoiling also, some energy is needed. So that loss is protected by this solid crystal. Okay. So when this occurs, no gamma energy is lost to the kinetic energy of recoiling nuclei at either the emitting or absorbing end of a gamma transition. So no gamma energy is lost to the kinetic energy of recoiling nuclei at either the emitting or absorbing end of the gamma transition. The recoilness recoil will not be occur at emitting end or absorbing end, so that there will be energy protection. Energy protection can be done by keeping the nuclei in a solid crystal. Okay. Gamma transition. Emission and absorption occur at the same energy. So that the emission and absorption will be occur at same energy. Okay. Resulting in strong resonant absorption. So it results in a strong resonant absorption. So here it should be noted that Moser effect cannot be observed in liquids and gases because the recoil energy cannot be dissipated in these states of matter. Okay. So this Moser effect cannot be observed in liquids and gases. So Moser effect cannot be observed in liquids and gases because the recoil energy cannot be dissipated in the states of matter. So as the recoil energy doesn't takes place in these liquids and gases, and because the energy cannot be dissipated in these liquids and gases, so it cannot be absorbed in these liquids and gases. Okay, what is Doppler effect? So Doppler effect or Doppler shift, we'll say Doppler effect or Doppler shift is the change in frequency or wavelength of a wave in relation to an observer who is moving related to the wave source. So what is Doppler shift? Is a change in frequency or wavelength of a wave in relation to an observer. As I am seeing, there will be a change in the wavelength or frequency. If it if you take an example of me who is seeing a wave relative to me, is if there is a change in the frequency and wavelength of the wave who is moving related to the wave source, that is a Doppler shift actually. So a common example is the change of pitch heard when a vehicle sounding a horn approaches and recedes from an observer. As we can take an example of a car which is horning. When we go closer to that, we feels that the pitch is hard, isn't it? Pitch heard is more. When we move away from that car, what happens? We feel that the pitch is low, isn't it? The sounding of horn is less comparatively when we approaches the car, isn't it? So that is what the Doppler effect is. As I am the observer, but the horn of the car is with the same frequency and wavelength. As I am moving related to the horn, what happens? If I go closer to that, I feel that the the pitch or the horn sound is more comparatively when I come back when I move far away from that um car, isn't it? Car and horn. So compared to the emitted frequency, the received frequency is higher during the approach. So compared to the emitted frequency, the horn is emitting the same frequency, but the receiving frequency is more when I go nearer to the car or horn, isn't it? Identical at the instant of passing by and lower during the recession. So passing as I am passing by, also the same identical instant will occur, but during the recession, as I go far away from that horn, there will be a less frequency. I will feel. Okay, that is what Doppler shift is. Doppler effect or Doppler shift is. Okay, so let us see the instrumentation. Before going to that, to understand uh, to understand this Mosber effect and appreciate the importance of this, we will consider an isotope of iron actually. So mostly we will consider an isotope of iron. So we'll consider an isotope of iron. The iron atom. So we will take the stable iron atom, stable isotope of iron, that is 57. Oh, shit. This one. Fe57. Sorry, I'll try to explain, sir. Okay. So we will take the example of a Fe57, that is mass number 57 iron atom, which is a stable isotope. So which is used more in Mosber studies actually. So there will be a decay to the cobalt. Actually, 57 cobalt uh, there occurs a decay of 57 cobalt, that is mass number 57 cobalt to Fe57 actually. So what happens? Cobalt 57, cobalt 57 decays. Okay, cobalt 57 decays to an excited iron atom. So cobalt 57 will decay into an excited iron atom. Iron will have, so iron which is in excited state, when it comes to the ground state, it emits a gamma radiation. It emits a gamma radiation or gamma decay, we will say. We have studied in the alpha, beta, and gamma uh, radiation. Sorry, gamma emissions we have seen. So whenever cobalt disintegrates or decays into iron of an excited state, it releases some amount of energy, that is gamma radiation, which is studied more in this one. The excited 57 Fe, the iron nuclei go directly to the ground state. It goes directly to the ground state by emitting 137 kilo electron volts of gamma ray. So firstly, actually, there is cobalt cobalt source will be there, that will be decayed into an iron. It decays to iron atom, iron element, which is in excited state. That excited state iron will disintegrate, or sorry, it comes to the ground state by releasing some amount of energy, that is 137 kilo electron volt of gamma ray. That is more, isn't it? The remaining 91%, so it releases 9% of this gamma ray of energy actually. So the remaining 91% of the transition takes place in two steps. It takes place in two steps. The emission of, after the emission of 123 kilo electron volt gamma ray, it emits 123 kilo electron of gamma ray. Come back, it takes 136 kilo electron volt from excited state to ground state. So the nucleus goes into intermediate excited state. The nucleus will go to the intermediate excited state, having a half-life of 10 to the power of minus 7 seconds. So the Fe goes to an intermediate state, that is 10 to the power of minus 7 seconds. It stays there and it will release. From that state, 57 nucleus, the 57 Fe nucleus reaches the ground state by emitting a low energy gamma ray of 14.4 kilo electron volts. It reaches to the ground state by releasing a 14.4 kilo electron volts. Okay. Let us put down this the factor which limit the precision of the energy value. This 14.4 gamma transition. Since the half-life of the excited state is known, the half of life, the excited state will be known. Okay. So we will try to figure out what is the energy difference. That is, we will find approximately 6 into 10 to the power of minus 9 electron volts of uncertainty in energy is found. Okay. So let us go to the instrumentation of this Mossberg effect actually. Let us see. So this is the instrumentation. This is the Mossberg drive. This is the collimator. This is the cobalt source. Just now we have seen the cobalt source, 57 cobalt. This is mass number 57 cobalt source. And this is the sample which we are using. So this is the detector. This is also sample. This is the collimator. This is the Mossberg drive. This is same as this one. So these are the detectors which are coming from the sample. They are detected by these detectors. Okay, instrumentation in the Mossberg spectroscopy. This is the instrumentation here. We can observe. Okay, Mossberg drive or absorber. So this is the Mossberg drive or absorber used to move the source relative to sample. So we can move this Mossberg drive relative to the sample. We can take the Mossberg drive closer or far away from the source, isn't it? So source is what actually? Source is here. Here the source is cobalt, isn't it? The source is cobalt here, 57 cobalt, mass number 57, cobalt, source of gamma ray emission, generally kept at Earth. Okay, so this is the source, which is mass number 57. Cobalt source is there. We will take this Mossberg drive will can be moved relative to the sample. Okay, relative to the sample, we can move that Mossberg drive. Collimator used to narrow the gamma rays. The collimator which is used here, these collimators are used to narrow the gamma rays coming from this cobalt source. The cobalt source releases some from the cobalt source. There will be reactions occurring in the cobalt source. After this reaction, there will be gamma rays emitting from this source. So there will be a collimator which will narrow these gamma rays. Coming gamma rays are narrowed by by using this collimator. Okay. Sample. So sample contains the sample to be analyzed. So it contains the sample must be analyzed, must be in solid phase and in crystalline structure. So it must be analyzed one. Sample must contains the sample to be analyzed one and must be in a solid or crystalline structure. Okay. So it should be in solid phase or in a crystalline structure. Usually requires large amount of sample. So it requires this instrumentation requires large amount of sample. It requires large amount of sample applied as thin layer on sample holder and irradiated. So applied as a thin layer on sample holder. On the sample holder, it is applied as a thin layer, okay, and it is radiated. Okay, so Mossberg drive, which can be moved related to the source, and source which contains 57 mass number of cobalt generally which emits a gamma rays, and a collimator which narrows the gamma rays, and a sample. First is a sample what the sample must contain. Sorry, the sample must be analyzed. This must be analyzed, and it must be in a crystalline structure or and solid phase. Okay, so the sample must be large amount. It must requires a large amount, and it is applied as a thin layer on the sample holder and is irradiated. Okay, and it is subjected to these gamma rays. Okay. Selecting a sample. How to select a sample in this case of Mossberg spectroscope? Let us see. Excited state should be relatively low energy. Excited state should be uh, of relatively low energy. It must be relatively low energy. Small change of energy between ground and excited state. There must be a small change between between the ground and excited state. Okay, too large change of energy results in no resonant emission. Okay, too large a change of energy results. If there is too large of energy change, there will be no resonant emission. Okay, there doesn't have a resonant emission. Okay, relatively long lasting life of excited state. Relatively must contain a long lasting life of excited states. Here the elements which are in a font of red, like this is K, potassium, iron, nickel, zinc, germanium. This is krypton, ruthenium. So these Ag is silver, tin, bismuth, tellurium, iodine, this wolfram. These are all these red font elements are used as Mossberg isotopes. These are Mossberg isotopes. Mostly we will use these shaded, blackly shaded red font elements only. Mostly these are used in the Mossberg spectroscopy. Here we can observe. So the figure shows the isotopes in which the Mossberg effect has been detected. These are the isotopes which elements are having this Mossberg effect. Okay, this Mossberg effect is detected in these red fonted elements. Okay, the elements of periodic table which have known Mossberg isotopes. The elements of the periodic table which have known Mossberg isotopes are shown in red font. These are having red font are known Mossberg isotopes. Okay, these are known Mossberg isotopes. Those which are used the most are shaded with black. These shaded black elements are isotopes are mostly used. Okay, mostly used in the Mossberg spectroscopy. So, how to select a sample? Select the excited state should be relatively low energy. The excited state must be relatively low energy, and there must occur a small change of energy difference. Okay, small change of energy difference between ground and excited state, and also there must not be any large energy result, which results in no resonant emission. There will be no resonant emission if the large change is there. So it must be a long lasting life of excited state. Okay, so these are the example of Mossberg isotopes. So detector, let us see detector. So here we have seen the sample. Now we are going to discuss about the detectors. Okay, so detector, choice of detector depends on gamma ray energy. So this choice of detector will depends on the gamma ray energies. Okay, cannot be seen using traditional examination methods of electromagnetic radiation. So these, by using a traditional examination of methods, we cannot see this gamma ray. Okay, gamma ray energies we cannot see. So cannot be seen using traditional examination methods of electromagnetic radiation. Observes observes effect of gamma rays on a material that observes them. So, so which can be observed, these effects of gamma rays on a material which absorbs them, which as the gamma rays were absorbed by the materials, that can be where we can observe these effects. Okay, resonance detectors. There will be resonance detectors. So distance and angle of detector is crucial. The distance and the angle of this detection is crucial in this detectors. Okay, there are two types. First is gas filled, and second one is scintillation. So these are two types actually. First one is gas filled one, and second one is scintillation. Here we will see the first one. Sensitive volume of gas between two electrodes is taken, not often used, not often, mostly used. This is sensitive volume of gas between two electrodes is taken in this one, but it is not used more often. Okay, so next one is, this is the gas tube method or type. So it is taken between two electrodes, but it is not morely used. Second one is scintillation. Scintillation material is a luminescent material. What is a luminescent actually? When an excited state, when it releases low whole light, isn't it? When when an electron absorbs energy and releases whole light, that is called luminescence. So here the sensitive material is luminescent material. Gamma rays interact with luminescent material. So sensitive material must be a luminescent material. So the detection material must be a luminescent material, and that gamma rays coming out of the gamma rays coming out of this sample is will interact with this luminescent material. So it will react with a luminescent material. Gamma rays are detected by an optical detector. So the gamma rays coming from the sample will be interacted with the luminescent material, and those are detected by the optical detector. Those are detected by optical detector. Usually used detector. This is most usually used detector, but as comparatively with the gas filled one. So this is the scintillator light pipe. This is photocathode, photoanode, and this is the photomultiplier tube, whereas photo is light is multiplied multiple times. Okay, so three quantities called hyperfine interactions are studied. So there will be studying of this effect in uh, three quantities. Those are called hyperfine interactions. So these are the hyperfine interactions. That is, first one is isomer shift. First one is what? Isomer shift. And second one is quadrupole shift. Okay. Second one is what? Quadrupole shift. So third one is magnetic splitting. Third one is what? Magnetic splitting. Or we can say nuclear Zeeman splitting or magnetic hyperfine splitting. There are three hyperfine interactions are there. Three quantities called hyperfine interactions are there. First one is isomer shift. Second one is quadrupole shift. Third one is magnetic splitting. It's nuclear Zeeman splitting or magnetic hyperfine splitting. Let us see the first one, isomer shift or chemical shift. Isomer shift or chemical shift. Here, if you see, arises due to the non-zero volume of the nucleus and the electron charge density due to the s electrons within it. Actually, when the chemical environment, when the chemical environment alters, when the chemical environment alters the energy separation between the ground state and the excited state of the nucleus, thereby causing a slight shift in the position of the observed resonance line. So this isomer shift, when it occurs, when there is a chemical environment change in that observer and the source, actually the observer, otherwise we can say the ground state and the excited state. If there is chemical environment change in this ground state and excited state, there might cause a slight shift in the position of the observed resonance shift. Okay, or observed resonance line. There will be resonance line where we can observe the slight shift in the position. Okay, there will be position of the shift will is changed in the observed resonance line. That occurs this isomer chemical shift. That is why there will be chemical change, chemical environment alteration is there. That's why we will call it, this isomer shift is also called as a chemical shift also, we can say. Okay, electric monopole or Coulomb interaction between nucleus, that is protons and electrons. There will be electron monopole, Coulomb interaction between this nucleus and electrons will occur. The shift will be different in various chemical compounds. This isomer shift is different in different chemical compounds, and that is also a reason to say that this is known as a chemical shift or chemical isomer shift. We can say that chemical isomer shift. Okay. It is also frequently referred to as the isomer shift or chemical shift. Isomer shift values gives information on the oxidation state. It gives the importance of the information about the oxidation state, spin state, and bonding properties such as covalency and electronegativity. This also gives information about oxidation state, spin state, bonding properties, and also covalency and electronegativity. So this is how isomer shift is important. This arises due to the non-zero volume of the nucleus and the electron charge density due to s electrons within it. Okay. It leads to a monopole, that is Coulomb interaction, altering the nuclear energy changes. So it leads to what? Coulomb interactions between nuclear energy levels. Nuclear energy levels is what actually protons and electrons. Okay. Energy difference in s electron environment. So energy difference in s electron environment between the source and observer thus produces a shift in the resonance energy of the transition, that is ground state and excited state. If there is any difference in the environment, that occurs this shift actually. Okay, any difference in s electron environment between the source and observer thus produces a shift. There will be shift difference in the resonance energy of the transition. Okay. This shift, this shift shifts the whole spectrum. So this shifts the whole spectrum positively or negatively, depending upon the S electron density and sets the centroid of the spectrum. So this shift in the resonance energy of transition shifts the whole spectrum actually. The whole spectrum is shifted positively or negatively on what dependence on the dependence of the S electron density. Okay, as the which in the positively or negative spectrum may happen due to the S electron density and the sets the centroid of the spectrum. Okay, as the shift cannot be measured directly, it is quoted relative to a known observer. So the shift cannot be measured directly. This shift cannot be measured directly. It is quoted relative to the observer. So it is taken related to the observer. Okay. Example is Fe Fe57 mass number 57 iron. Mass based spectra will often be quoted related to alpha iron at R. So this is quoted against the alpha iron. Okay. It is useful for determining valence states. So this chemical shift or isomer shift is useful uh, for determining the valence states, ligand bonding states, electron shielding, and electron drawing power of electronegative groups. Example, so it can be useful for what? Can be useful for valence states, ligand bonding states, electron shielding, and electron drawing power for electronegative groups. Okay, so we can take an example of electron configurations of Fe2 plus, Fe3 plus are 3d6 and 3d5 respectively. For Fe2 plus, that is 3d6, and Fe3 plus 5, that is 3d5. Ferrous irons, ferrous ions have less electrons at the nucleus. So these ferrous ions will have less electrons at the nucleus due to greater screening of d electrons. So ferrous ions have less electrons at the nucleus due to greater screening of the d electrons. Okay. Thus, ferrous ions have largest positive isomer shifts. So due to this greater screening of d electrons, what happens? Ferrous ions have larger positive isomers. This will be having larger positive isomers shifts than the ferric ions. The ferrous ions will have a larger positive shifts. Okay, isomer shifts. This is about the chemical shift. Next one is a quadrupole splitting. This is the quadrupole splitting. You can observe here. Nuclei in states with an angular momentum quantum number I greater than half have a non-spherical charge distribution. This produces a nuclear quadrupole moment. So nuclei which is having angular momentum I greater than half. So the nuclei states which are having angular momentum greater than half have non-spherical charge distribution. There will not be a spherical charge distribution to the nuclei which are having angular momentum greater than half. So these type of nuclei will produce a nuclear quadrupole moment. We have seen in electric quadrupole moment in the earlier classes also. So in presence of an asymmetrical electric field. So in presence of an asymmetrical electric field produced by an asymmetric electronic charge distribution or ligand arrangement. That symmetric electric field is nothing but produced by uh, which is produced by an asymmetric electronic charge distribution or ligand arrangement. Okay. In presence of an asymmetric electric field, this splits the nuclear energy levels. So in the presence of this asymmetric electric field, there will be a splitting of nuclear energy levels will occur. the charge distribution is characterized by a single quantity called electric field gradient. So, so this charge distribution will be characterized by what? By a single quantity, that is electric field gradient, EFG we will say. So this charge distribution is characterized by this electric field gradient. Let us see this. In case of an isotope with a I greater than 3 by 2. So in case if an isotope is having angular momentum, angular momentum number I which is greater than 3 by 2, that ES such as Fe57 or SN119 or Fe57 or 119 SN, the ES is split into electron state, is split into two substates, ML plus or minus half and ML plus or minus 3 by 2. Okay, can be split into two types, two states. One is two substates, ML plus or minus half and ML plus 3 by 2. That is, the figure gives two line spectrum or doublet. Here you can observe this is the excited state, this is the ground state, this is the ferrous atom, which is having a mass number 57. This is the quadrupole moment, angular momentum number, that is I is equals to 3 by 2. Consider it releases and it goes to the ground state. When it isomer shift occurs and it goes from the ground state to the excited state. So this the quadrupole splitting is here. It may go from half to plus half or plus half to plus 3 by 2. The energy difference between this delta EQ can be taken. So there will be two substates, right? They are split into two substates, that is plus half, ML is equals to plus half, or else ML equals to plus 3 by 2. Okay. This is called the doublet spectrum. You can say it as doublet spectrum. This is the quadrupole spectrum. Okay. Next is magnetic splitting. In presence of magnetic field, the nuclear spin moment experiences a dipolar interact with the magnetic field. That is Zeeman effect. So, in presence of magnetic field, what happens? The nuclear spin moment experiences a dipolar interact with magnetic field. There will be nuclear spin moment experience a dipolar interaction with the magnetic field. Okay, in the presence of magnetic field, this nuclear spin will be interacting with the magnetic field. That is called what? That is the Zeeman effect, we will say. So whenever a nuclear spin moment experiences a dipolar interact the magnetic field, that is Zeeman effect. There are many sources of magnetic fields. So there are many sources of magnetic fields that can be experienced by the nucleus. Nucleus. Total effective magnetic field at the nucleus, that is B effective. We will take it as B effective is given by. So total magnetic field at the nucleus, B effective is given by B effective is equals to B constant B effective is equals to B constant plus B orbital plus B dipole plus B applied. So B effective is the sum of is all magnetic fields. Okay, B constant, B orbital, B dipolar, B applied. What are these? We'll try to study here. The first three terms being due to the atom's own partially filled electron shells. The first three, constant, B orbital, and B dipolar. These are due to due to the own the same atom which is partially filled. Due to the partially filling of these cells, these three will occur. Okay, the next one is due to the external. So B constant is due to splitting on those electrons polarizing the spin density of the nucleus at the nucleus. So B constant is due to what? Due to the spin on those electrons polarizing the spin density at the nucleus. Okay. B orbital is due to the orbital momentum on this electrons. Due to the orbital momentum of those electrons, B orbital is there. B dipolar is due to the spin of those electrons. Due to the spin of the electrons, B dipolars. There. This magnetic field splits nuclear levels with a spin of I into 2L plus 1 substrates. So this magnetic field splits nuclear levels with a spin of I into 2L plus 1 substrates. This magnetic splits will be of 2L plus 1 substrates. Okay, 2L plus 1 substrates. This is shown in Fe57 figure. This is the Fe57 figure, which is shown here. This is the excited state. This is the ground state where angular momentum I is equals to 3 by 2. There will be isomer shift and there will be magnetic splitting from ground state of half to excited state of 3 by 2, 1 by 2, and minus 1 by 2. And also from minus 1 by 2 to 1 by 2, and minus 1 by 2 to minus 1 by 2, minus 1 by 2 to minus 3 by 2. Whole, there will be 12 plus 1 substrates will be there. Okay. So these interactions, isomer shift, quadrupole splitting, and magnetic splitting, alone or in combination, are the primary characteristics of many Mossberg experiments. So these are the three reasons for either isomer shift or quadrupole splitting or magnetic splitting are individually the reason for the magnetic Mossberg effect, or the combination of chemical shift quadrupole or magnetic field or magnetic field quadrupole, these combinations are the primary characteristics of this Mossberg spectra. Okay, these are the primary primary combinations and primary characteristics of the Mossberg spectrum. Mossberg spectroscopy is useful analytical tools for studying a variety of systems and phenomena. So this is used in used in useful in analytical tools for studying variety of systems. Systems. So these Mossberg effects are used in variety of applications. Okay. So these are used in variety of applications. Like I give some examples. So what we have discussed the Mossberg effect. So these are used in many applications like material sciences. We are used in material sciences, studying phase transitions, magnetic properties, and also local atomic environments in materials. Okay, these are used in material science, chemistry, biology, and mineralogy. So In the material science, what we will do by using this Morpher effect, we'll study the phase transitions and also magnetic properties and also local atomic environments in materials. Okay. So in chemistry, we will investigate the chemical bonding. As we have seen in the earlier slides itself, we have we will investigate chemical bondings, oxidation states, and also structure of molecules. We can study the structure of molecules by using this mass spectroscope. In biology, we can study the properties of iron containing biomolecules like hemoglobin. We have seen the hemoglobin example also. In mineralogy, also, we can examine the valency states of iron in minerals. So, valency states of iron in minerals can be studied in mineralogy. So, mass-based spectroscopy uses gamma ray absorption to probe local electronic environment of nuclei, providing information about the chemical structure and magnetic properties of material. Okay. So these are the applications of this mass-based spectroscopy. So we will try to examine the valence states of this iron also, iron, which is found in nature as FeO, actually Fe0, but we'll try to Fe0, Fe2 plus, Fe3 plus. So we'll try to study the valence states of this iron. Okay, this is about today. In the next class, we are going to study about NMR spectroscopy, NMR spectroscopy, and that will be the last class of our series of lectures. So, thank you.